Welcome to G Fun Facts Online. Today we're talking about powering the moon. As humanity plans to establish a permanent presence on the lunar surface, we face a fundamental problem: energy. The moon is a world of extremes. It has 14-day-long nights with unimaginable cold, followed by 14 days of searing sunlight. A permanent human outpost can't rely on solar power alone. The solution being developed by space agencies is both audacious and complex: building a nuclear fission reactor on the moon. This isn't just about shrinking down a power plant from Earth, it's a monumental engineering challenge. Let's dive into how we plan to power a new world. The biggest reason for lunar nuclear power is the moon's brutal environment. The 29.5-day cycle of light and dark means any solar-powered base would need to store enough energy to survive for 2 straight weeks without sunlight. That's a huge challenge for even the most advanced batteries. But it's not just about the long nights. Some of the most interesting places on the moon, the permanently shadowed craters at the poles, never see sunlight at all. Scientists believe these craters hold vast quantities of water ice, a resource absolutely critical for life support and for creating rocket propellant. To access this ice, you need a power source that works in total darkness. A nuclear reactor is the perfect fit. It would enable 24/7 operations, power massive scientific instruments, and drive the technologies needed to live off the land, like 3D printing structures from lunar soil or extracting oxygen from rocks. The experience we gain would also be invaluable for future missions to Mars. NASA's current program, called the Fission Surface Power Project, or FSP, builds on decades of research. Its most direct predecessor was the Kilopower Project, a joint effort with the Department of Energy that started in 2015. The highlight was the Krusty experiment in 2018, that's Kilopower reactor using Stirling technology. This ground-based test proved that a small, self-regulating reactor was feasible. The Krusty reactor used a solid uranium-235 core, about the size of a paper towel roll, and safely generated power. It even demonstrated the ability to shut itself down safely in case of a malfunction, a critical feature for an autonomous system. Building on that success, the Fission Surface Power Project is much more ambitious. The goal is to develop a 40-kilowatt reactor that can operate on the moon for at least 10 years without any human help. 40 kilowatts is enough power to run about 30 average US households continuously. In 2022, NASA awarded contracts to 3 different companies to come up with initial designs. Those companies are Lockheed Martin, Westinghouse Electric, and a joint venture called IX, formed by Intuitive Machines and X Energy. NASA set a strict weight limit of 6 metric tons for the entire system and mandated that decade of autonomous operation. The agency plans to pick a final design and have a reactor ready for launch by the early 2030s. So what makes this so hard? Let's break down the Herculean engineering tasks. First, there's the tyranny of the rocket equation. Every single kilogram launched to the moon is incredibly expensive and difficult to get there. That 6-ton weight limit for the entire system, reactor, shielding, cooling, everything, is a massive constraint. The reactor has to be compact enough to fit in a rocket fairing and tough enough to survive the violent vibrations of launch. Once it lands, how do you deploy it? One idea is to land it on a rover, which would then drive it a safe distance away from the main habitat. Another is to have a lander drop it off and then have robots move it into place. A particularly clever idea for shielding the reactor is to simply bury it under several meters of lunar regolith, or soil. This would provide a natural and highly effective barrier against radiation, but it means we have to figure out how to excavate on the moon, a task we've never attempted before. Next, the reactor has to survive the hostile lunar environment. With no atmosphere, temperatures swing wildly, from 127 degrees Celsius in the sun to negative 173 Celsius in the dark. In those permanently shadowed craters, it can drop to negative 250 Celsius. Materials become brittle, and electronics can fail. Cooling the reactor is a major hurdle. On Earth, we use massive amounts of water. On the Moon, that's not an option. A lunar reactor must use radiators to reject its waste heat into the vacuum of space. This is far less efficient than cooling on Earth, meaning the radiators have to be huge, and they are one of the heaviest parts of the system. The more efficient the reactor, the less waste heat it produces, and the smaller and lighter the radiators can be. And then there's the lunar dust. It's a fine, abrasive powder, like flour, but with the sharpness of microscopic glass shards. It's electrostatically charged, so it clings to everything. During the Apollo missions, it scratched helmet visors, fouled seals, and clogged instruments. For a reactor, it could coat the radiators, crippling their ability to shed heat, or work its way into moving parts, causing them to jam. Engineers are developing solutions like electrodynamic dust shields that use electric fields to repel dust, special nano-coatings, and robust seals for all mechanical components. Perhaps the most ambitious goal is the requirement for 10 years of autonomous operation. The reactor must start up, manage its power output, and shut down all by itself. It must also be able to diagnose and respond to any problems without human help. The communication delay between Earth and the Moon makes real-time remote control impossible. This requires an incredibly advanced reactor instrumentation and control system. Think of it as an AI for a nuclear reactor. It will have a protection system to automatically prevent unsafe conditions and a control system that manages day-to-day operations using advanced algorithms to anticipate problems before they happen. At the heart of the machine is the reactor core. This is where fission happens, generating immense heat. NASA is specifying the use of low-enriched uranium, or LEU, not the highly enriched, weapons-grade material used in some older designs. This reduces proliferation risks. The fuel itself will likely be a ceramic, like uranium dioxide, encased in a tough metal cladding. A key challenge here is fuel swelling. Over a decade of intense radiation, the fuel pellets can expand, putting stress on the cladding. Some analysts believe this could be a limiting factor, potentially capping the reactor's lifespan. Once you have all that heat, you have to turn it into electricity. This is the job of the power conversion system. There are two main technologies being considered. First are Stirling engines. A Stirling engine uses a sealed gas, like helium, to drive a piston. They are very efficient and have few moving parts, which increases reliability. The Krusty test used them, and Lockheed Martin's design is expected to as well. The second option is a Brayton cycle converter. This is essentially a small closed-loop gas turbine. An inert gas is heated by the reactor, expands through a turbine, and spins an alternator to make electricity. It's a mature technology that is highly scalable. The final choice will depend on a complex trade-off between efficiency, mass, and reliability. Of course, a nuclear reactor produces intense radiation. Shielding both astronauts and sensitive electronics is critical. The problem is that shielding is heavy. For neutrons, you need materials with light atoms, like lithium hydride. For gamma rays, you need dense materials with heavy atoms, like tungsten. The design will use a layered combination of these. But as mentioned, the most elegant solution is to use the Moon itself. Burying the reactor under the regolith would provide all the shielding you could ever need, dramatically reducing the launch mass. This whole endeavor is not happening in a vacuum. A new space race is heating up. China and Russia have announced joint plans to build their own lunar base, also powered by a nuclear reactor, with a target date in the mid-2030s. This has lit a fire under the US government. Internal NASA directives have reportedly called for an acceleration of the Fission Surface Power project, aiming to have a reactor on the Moon by 2030. The concern is that the first nation to establish a permanent, powered presence could gain a strategic advantage, potentially controlling access to valuable resources. Finally, there's a crucial challenge we can't ignore. What do you do with the reactor after its 10-year life is over? On Earth, decommissioning a nuclear plant is a long and expensive process. On the Moon, the most likely scenario is in situ decommissioning, leaving it where it is. This is what was done with the small radioisotope power sources left by the Apollo missions. But a fission reactor is far more radioactive. One option is to bury the entire spent reactor deep under the lunar soil, effectively creating a permanent disposal site. This would require advanced robotics for excavation and entombment. The long-term management of nuclear waste is a major challenge here on Earth, and it will be no different on the Moon. Any plan must include a credible strategy for the reactor's end of life to ensure we don't leave a legacy of radioactive contamination for future generations. The development of a lunar nuclear reactor is a testament to the human drive to explore. The engineering hurdles are immense, from autonomous control to rejecting heat in a vacuum. But the potential rewards are equally great. A reliable, continuous power source on the Moon would unlock a new era of science and exploration, enabling a permanent human presence on another world, and creating a vital stepping stone for our journey to Mars and beyond. The coming decade will determine if we can turn this science fiction vision into a lunar reality.